Welcome once again to this second part of Clipper circuits. In the presentation previous to this, we have seen what Clipper circuits are and we have solved various examples which falls under the category of series Clippers. In this presentation, what we would try to look forward is the shunt Clippers. Right? So let us start with the presentation. So what are the shunt clippers? In series clippers, we had seen that the diode was present in series to the load resistance. In the shunt clipper, the diode would be present in shunt to the load resistance. That is, the output would be taken across the diode. So the portion of the circuit where the output is taken, diode would actually be the part of this. Let us try to take a simple example of a shunt clipper. Let us try to see this circuit. In the series clipper, we had seen that the diode usually was present in this branch or in this part of the circuit. Here, the diode is present here. The output is taken across the diode. So, this gives the name to the circuit as shunt clipper. Again, for this circuit we consider the same input available between A and B given to the circuit, which is a sinusoidal signal. And let us try to estimate what would be the output voltage. We would try to follow again our three-step approach for solving the clipper circuit. What is the first step? The first step is to identify that when the diode is on, what would be the output voltage, and when the diode is off, what would be the output. Here, if we see that when the diode is on, diode acts as a closed switch. Diode acts as a closed switch, and if the diode is ideal, then there would not be any voltage drop across this diode, and it acts as a short circuit. So this whole branch acts as a short circuit. It means that the output voltage would be zero. So when the diode is on, output voltage would be zero. And when the diode is off, suppose that this diode is off, then it acts as an open switch. If it acts as an open switch, there would not be any current which will be passing through this loop. And if there is no current which is passing in this loop, the voltage across this resistor would be zero. In this case, the input voltage is available between A and B. There is no voltage across this resistor R. So the same input voltage would be available between these two terminals. That is, the same voltage would be available at V0. So when the diode is off, V0 would be same as Vin. And when the diode is on, V0 would be 0. So I can write it like this. When the diode is on, it acts as closed switch, V0 would be equal to 0. When the diode is off, it acts as an open switch, no current flows, V0 would be equal to Vin. This is primarily the step where series clipper and shunt clipper differs. Going to step 2. Identify the condition for the diode to be on and off with respect to your input voltage. Again, we understand that the voltages at P terminal should be higher than the voltages at N terminal. So, in the positive half cycle, A would be positive, B would be negative, and hence the voltages on P terminal would be higher compared to the voltages at N terminal. So, in the positive half cycle, diode would be on, and in the negative half cycle where A would be negative and B would be positive, your N terminal would have higher voltages, P terminal would have less voltages, and hence the diode would be off. So the diode would be on in positive half cycle and the diode would be off in negative half cycle. So from step 1 and step 2, we can write step 3, estimating what would be the output waveform. So in the positive half cycle, that is when Vin is greater than 0, when Vin is greater than 0, diode is on. We know that when the diode is on, output voltage is equal to 0. So when the diode is on in the positive half cycle, output voltage would be 0. And in the negative half cycle, diode would be off. Diode would be off. And if the diode is off, output voltage is same as input voltage. So if we try to draw the output waveform, would be something like this. During the positive half cycle, I don't get the output voltages. During the negative half cycle, output voltage is same as the input voltage. Again, in a positive half cycle, I don't get output voltage. Negative half cycle is reproduced in the same way as the input. Fine. If I try to give name to this, we know this is a shunt clipper, and the positive portion of the waveform, the upper portion of the waveform is clipped, so we would call it to be a positive shunt clipper. Maybe at this point, you can pause the video, you can go through the slide once again, and you can again analyze this. The method of analysis remains the same. The only context is that instead of series, now the diode is present in shunt position. If we are true, we can again go to the next example. Let us try to take this example, where we are adding a DC source. So this would be an example of a biased clipper. Again, the diode is in shunt. The output is taken across the diode. So diode is in shunt. So this is again an example of a shunt clipper. Again, we move on with the same assumption that the maximum input voltage that we have are more than VB, right? So VB is less than the maximum input voltage that we have. Now, we would again try to estimate what would be the output voltages using our three-step approach. Now, because you have a background of series clippers, we have discussed one basic example of shunt clipper. I am sure you would be able to solve this and identify the value of output voltage. So again, I would request you to pause the video here and work in this three steps. Try to take your pen and notebook, work out these three steps and try to estimate the output voltage. Yes, so you may pause the video, and once you are done with it, we can restart. Very fine. I am sure you would have worked out this, and many of you would have got the correct answer. Fine. Let us try to analyze this. The first step, identifying that when the diode is on, it acts as a closed switch. So this is a short circuit. But now the output voltage taken between these two diode is a closed switch. So the output voltage would be same as minus VB, which in earlier case was 0. Now because the battery is present and because the battery is having a negative polarity here, I would say that the output voltage would be equal to minus VB. Similarly, when the diode is off, there is no current which would pass, so no voltage drop across R. So the same input voltage would be available between these two terminals, and these are the terminals between which output voltage is measured. So output voltage would be same as input voltage. So when the diode is off, output voltage would be same as input voltage, and when the diode is on, output voltage would be restricted to minus VB. Going to the next step, identifying the condition for the diode to be on and off. Again, we say that the voltages at P terminal should be higher than the voltages at N terminal. What are the voltages available at P terminal? Input voltage Vn. What are the voltages available at N terminal? Minus VB. So when the input voltages are greater than minus VB, diode would be on, and when the input voltages are less than minus VB, diode would be on. So combining step 1 and step 2, we can estimate the output waveform in step 3. That is, when input voltages are greater than minus VB, diode is on, and when the diode is on, output voltage is minus VB. And when the input voltages are less than minus VB, diode is off. In that case, output voltage would be same as Vn. If you try to look at this in terms of the waveform, then I have redrawn the input voltage here. I have drawn a line of minus VB because the polarity of the battery has been changed. This is minus VB. So I have a condition where this part of the input waveform is greater than minus VB, whereas this part of the input waveform is less than minus VB. We know that when the input is greater than minus VB, my output is freezed at minus VB. So during this portion, my output is freezed at minus VB. During this portion, diode is off, and when the diode is off, the input voltage would appear on the output side. So this portion of the input waveform should be appearing on the output side. Again, the diode is on, so this should be freezed to minus VB. Again, this portion of the input waveform should be appearing at the output side. So if we see the output waveform, this is the kind of output waveform we will get. When input is higher than minus VB, it is restricted. If input is less than minus VB, it is allowed to pass. Higher than minus VB, restricted. Less than minus VB, allowed to pass. Right? If we try to classify this, then this is a shunt clipper, this is a biased clipper, and as the upper portion of the waveform is clipped, we would call it to be a positive clipper. So combinedly, we would call it to be a biased positive shunt clipper. If required, you may take a pause here and you can compare your answer with what we have done. I am sure you would be able to understand it clearly. Fine. Going to the next example, let us try to take an example where we have two sources, VB1 and VB2, and we are using two diodes. This example is basically an example of a dual level clipper circuit, where some portion of the positive part of the waveform would be clipped, as well as some portion in the negative part would be clipped. It means that upper portion would also have some clipping, lower portion would also have some clipping, right? Whatever be the case, we can analyze this again in our basic 3 steps. What are this? Identify the output when the diode will be on and off. Now, here we would have to comment about the on and off conditions of two diodes, D1 as well as D2. Right? So if we talk of D1, if the D1 diode is on, we have to remember the basic fundamental that the voltage in the branches which are parallel would always remain same. The voltage in the branches which are parallel would always remain same. It means that the output voltage, the voltage in this branch which is consisting of D2 and VB2, and the voltages across this branch which is consisting of D1 and VB1 would be same. So if D1 is on, then the voltage between these two terminals would be VB1. So the same voltage would be here and the same voltage would be available at the output. Similarly, if D2 is on, then the voltage between these two terminals is minus VB2, and hence output voltage would be minus VB2. And if both the diodes are off, then there would not be any current which would be passing. So voltage across this resistor R would be 0. In that case, output voltage would be same as the input voltage. And we would see once you complete this discussion, you would see that there would not be any chance where both the diodes would be on. Actually, it would not be. Right? So in the first step, we identify that diode 1 is on and diode 2 is off. D1 is on, D2 is off, V0 would be equal to VB1. When D1 is off and D2 is on, V0 would be equal to minus VB2. And when both the diodes are off, V0 would be equal to Vn. In step 2, we identify the conditions when diode would be on and when the diode would be off. Now if you think of diode 1, then N terminal is connected with plus VB1, P terminal is connected with Vn. So when input voltage is greater than VB1, D1 would be on. When the input voltage is less than VB1, D1 would be off, because the potential at P terminal should be larger. So if input voltage is greater than VB1, then D1 is on, otherwise it is off. Similarly, if we talk of D2, then to D2, the P terminal is given the voltage VB2. N terminal is given the voltage Vin. So this voltages, P terminal voltages should be larger than N terminal voltage for diode to be on. Right? So when input voltage is less than minus VB2, when input voltage is less than minus VB2, D2 would be on. Let us try to see this. Right? So D1 would be on when input voltage is greater than VB1. This is my VB1, this is my input voltage. When input voltage is greater than VB1, voltage at P would be higher than voltage at N, so diode 1 would be off. Otherwise, sorry, diode 1 would be on. Otherwise, it would be off. Similarly, D2 would be on. D2 would be on if input voltage are less than minus VB2. So P terminal voltage are minus VB2, N terminal voltage are input voltage. If input voltage is less than minus VB2, then the voltages at P terminal are higher than the voltage at N terminal, and hence the diode would be on. Otherwise, it would be off. Now, from these two conditions itself, you would be able to identify that there are no chances that D1 and D2 would simultaneously be on. Yes? Yes. Let us go to the third step, that is estimating the output waveform. So, if the input is greater than VB1, if the input is greater than VB1, diode 1 would be on. And if the diode 1 is on, V0 would be equal to VB1. This is what we have stated in the first step. If the input voltage is between VB1 and VB2, that is, input voltage is less than VB1 but greater than minus VB2. So, if the input voltage is less than VB1, then diode 1 would be off. Similarly, if the input voltage is greater than minus VB2, then diode 2 would be off. It means that both the diodes would be off. So in this case, the output voltage would be same as the input voltage. The third condition of step 1. And the last part, that is when input voltage is less than minus VB2, D1 would be off, D2 would be on, and V0 would be equal to minus VB. If you look at this in terms of the waveform, it would be more easy to understand, right? So I have again redrawn the input waveform. I have drawn two voltage levels. One is VB1, VB1 is positive, VB2 is negative, so I have drawn it as minus VB2. So this portion is the waveform where input voltage is greater than VB1. So this is the case. The diode 1 would be on and D2 would be off. And what would be the output? Output would be VB1. So I would get a flat output here, which would be restricted at VB1. Right? During this portion, when the input voltage is less than VB1 but greater than VB2, the input voltage, this blue line, is less than VB1 but greater than VB2. So in this case, what would be the case? Both the diodes would be off, and hence the output voltage would be same as input voltage. So you expect that in the output, you expect this line to appear, to come. This portion of the input signal would appear. Third case, when the input is less than minus VB2. So when the input is less than minus VB2, D2 would be on, D1 is off. So output would be restricted to minus VB2, right? So if you try to estimate what would be the waveform would be something like this. You know, between this VB1 and VB2, if the value of input is between VB1 and VB2, you would get it in the output. But if the input has a value which is less than minus VB2 or higher than VB1, then it gets clipped, right? So we identify that the upper portion is also clipped, the lower portion is also clipped, and hence the name given dual level clipper, right? So by this or with this, we cover almost all the varieties that we have in case of clipper circuits. Many of the examples based on what we have discussed are given as a part of your assignment. You can always solve it. There I have made a small change, which is instead of a sinusoidal signal, I have given you a triangular signal, but that should not be a matter so far as analysis of the clipper circuit is concerned. Once again, thank you for joining. Thank you.